This conference will now be recorded.
Welcome everybody to the GEO AquaWatch webinar. Today's webinar will be on the GLORIA Dataset. My name is Dr. Mary Beth Neely. I'm the scientific coordinator for GEO AquaWatch, and I do apologize for being under the weather today. So I'll make it short and sweet. Our first speaker is Dr. Nima Palavan. He's principal scientist for the Freshwater Sensing Program at NASA. And then following Nima will be Daniela Gerlin. She's a natural resources research scientist, formerly with Wisconsin Department of Natural Resources. Following Daniela will be Moritz Lehman. He's a senior oceanographer with Starboard Maritime Intelligence. And rounding out the speakers will be Daniel Maciel, environmental engineer, instrumentation laboratory for aquatic ecosystems at INPE.
Awesome. Thank you, everyone, for attending this webinar. So again, my name is Nima Palavan. I'm a lead scientist with the Freshwater Sensing Program at SSAI based at NASA Goddard Space Flight Center. It's my pleasure to start this tag team presentation. GLORIA Dataset started several years ago, and we're very happy to see this dataset being used by many scientists, students, PIs across the world in many countries, and to be able to hopefully advance the state of the art within the aquatic remote sensing domain. Next, please, Moritz. Yeah. So this is basically, I'll be covering mostly the history of GLORIA. Daniela will be talking about the metadata and the data set itself. Moritz will be speaking about the QC of the data, and Danielle will finish up with some demonstration of the GLORIA data set. So GLORIA was born out of the atmospheric correction into comparison exercise in 2018. Back then, Eric Vermote and Jean-Claude Roger, good friends and colleagues of mine, invited me to be part of this exercise as the lead for the aquatic component of the ASICS, or atmospheric correction into comparison exercise. And then Antoine Manger from the European side was also invited by Ferran Gascon and Georgia Daxani to also co-lead this effort. Back then, we started off by discussing the utility of to evaluate the utility of 8 different atmospheric correction processors applied to Landsat 8 and Sentinel-2 data, and the focus of our, can you go back please, next? Yeah, back, but it's okay, yeah. So, and then basically the idea was to just focus on the aquatic side of the house, because this round of ASICS was the second round of ASICS, and the first round was primarily focused on terrestrial applications, and then this component was added in 2018. Next, please, Moritz. There we go. So, of course, the obvious starting point for the ASICS and the assessment of 8 different atmospheric correction processors was to use AeroNet OC, AeroNet Ocean Color data sets, for evaluating those 8 different atmospheric correction processors, and primarily in coastal waters. But we knew that this data set would not be adequate, although they are excellent source for evaluating various atmospheric correction processors. So for that matter, we thought that we should start a data drive. And back then, and then in 2018, after October, when we had our first workshop, we sent out an announcement through IOCCG and essentially requested different PIs, different scientists who might have some radiometric observations coincident with Landsat 8 and Sentinel-2 overpasses. Next, please. Yeah. So after the announcement went out, we received positive responses from more than 15 institutions, and they contributed to this A62 data set. And then the data set was additional to the AeroNet OC matchups. So we provided a template to these different institutions and PIs, and those essentially um, metadata templates would essentially include ancillary information like latitude, longitude, time, instrument methodology, and many other variables, including water quality data sets, in addition to, of course, radiometric spectra. Next. So after putting all these data sets together, in about April, May of 2019, almost 6-7 months after the start of the exercise, we had over 3,000 in situ radiometric observations that would potentially match with Landsat 8 and Sentinel-2. So this global map here is a map that I shared with folks and with the audience at the IOCS meeting in Busan, and also at the LPS meeting in Milan. Back then, just less than a third of this data set was actually matching and sort of providing valid data sets and matchups along with Landsat 8 and Sentinel-2. So that was of course a bummer, but we had to live with this small data set for the assessment of those atmospheric correction methods. That being said, internally in our team, we had some interest in algorithm development, and we, for say, chlorophyll A retrievals and other water quality variables, and initial attempts, as part of the initial attempts, we used some simulated data sets to develop algorithms, and things did not work well. For that matter, we started using this sort of extended A6 sort of data set, as you know, the numbers were back then about 3,500 records, and we started seeing some good retrievals using machine learning methods that we have started publishing in 2019 or 2022. Next, please. And long story short, the results were fantastic. The algorithm retrievals and performance assessments were quite successful. So we were quite encouraged by the results. For that matter, I started reaching out to many more individuals, many more PI scientists across the world. Whoever I knew, I sent out cold emails to people and requested data sets. And the data grew up to about 5,400 number of records by the end of 2020, early 2021. And by that time, we had already published several papers in collaboration with all the data contributors. Next. So in 2021 timeframe, early time, then maybe February, March, I thought this was about the right time. After publishing a couple of papers and sort of seeing all the encouragement and hearing all the sort of feedback from colleagues from all over the place, I thought this was the right time to essentially let the data set go public and essentially provide the data set to the broader community. And so back sometime, maybe May or June, I started reaching out to all the PIs, making sure that everyone is on board, everyone is happy with the data being shared as part of the data publication. And the response was overwhelming, fantastic. Over 95% of the individuals agreed to the release of the data set. So in October of 2021, I reached out to all of them. I called for a meeting, and I basically just didn't have time to pursue this work, and I requested for volunteers. And Moritz and Daniela stepped up and volunteered to be co-leading this effort and essentially putting the data sets together, doing the further QC and QA of the data sets, and also write up a sort of a descriptor for the data. And with that, I'll let Daniela speak to the data set and be happy to answer any questions at the end. Thank you.
Hello, everybody. I would just like to ask Moritz to continue sharing the slides, even though I'm pretty certain I tried advancing the slides on the playback screen instead of my actual presentation. And can you go back one slide? So we eventually released an open access dataset of over 7,500 remote sensory reflectance RRS and co-located water quality measurements in a collaborative effort of researchers affiliated with 59 different organizations, together with our data descriptor in scientific data in February 2023. And these researchers were either contributing their field measurements to the GLORIA dataset, they were involved in coordinating the effort of working on the data descriptor on the GLORIA dataset, involved in readying the CBAS data included in the GLORIA dataset, or supporting the quality control of the radiometric data. Next slide. Next slide, please. Okay, thanks. The variables in the GLORIA dataset include the chlorophyll A concentration, the chlorophyll A plus pheophytin concentration, which is more typical for spectrophotometric measurements, the TSS concentration, the absorption of CDOM at 440 nanometers, the turbidity, Secchi depth, aerosol optical transparency, remote sensory reflectance, and then radiometric component spectra. The ancillary data includes the latitude, longitude, date, time, elevation, wave height, wind speed, cloud fraction, and depth. And next slide, please. The data was acquired in part from the CBAS Biooptical Archive and Storage System CBAS, and we are looking at 1,206 CBAS entries there, and then the data contributors, and we are looking at 6,366 data entries there. The RRS measurements represent an almost global latitudinal and longitudinal range, spanning at least 475 different water bodies in 28 countries over a time frame of 32 years. And these measurements include mostly from lakes, with 59.6%, followed by coastal oceans, estuaries, rivers, and others. And these others include some of our Norwegian fjords, Scottish lochs, some sewage ponds, and some aquaculture ponds. Next slide, please. So we released, as aforementioned, an open access dataset of these over 7,500 hyperspectral remote sensory reflectance measurements from at least 475 different water bodies, spanning 6 out of the 7 continents. The sampling locations are shown in this map. Next slide, please. The radiometric data currently entail 7,572 remote sensory reflectance measurements ranging from sediment, chlorophyll, and or CDOM dominated to clear inland and coastal waters, and the water quality attribute data currently comprise several thousand chlorophyll A, TSS, CDOM for 40 turbidity and Secchi depth measurements from the same water bodies. Next slide, please. If you're looking at the GLORIA dataset in detail, we will encounter many different files, most of them CSV files and one MS Excel workbook. And if you're looking at the first set of files, we're looking at all the measurements of the downwelling irradiance, the upwelling, or the sky radiance, the total radiance, the upwelling radiance, and the water leaving radiance at 1 nanometer intervals from 350 to 900 nanometers or less as available in different CSV files. And the way these radiometric quantities are related to our instrument setups for the radiometric measurements is shown in the graphic to the right. The downwelling irradiance data is reported above the surface. It can actually come from measurements above water or in water, and the in-water measurements would have been extrapolated across the surface to derive the downwelling irradiance and reported above surface. And the L sky and LT are from one of our typical above surface radiometric measurement setups, and the water leaving radiance LW is from one of our near surface setups using a skylight blocking technique, and then the LU 0- and UZ are actually combined in the LU, and these are extrapolated across the water surface and then reported as above water quantities. The next file is related to the metadata and water quality. No, not the next slide, only the next file. To the metadata and water quality measurements associated with each RS spectrum. And this information is found in the GLORIA Meta and Lab CSV. And this file includes the GLORIA unique sample ID and then the metadata, a lot of information regarding the radiometric measurements. It includes the radiometric methods, the water sample collection information, all of the laboratory methods with some short names, and then the water quality attributes themselves. Then we have two additional files related to the binary quality control flags for each QC procedure. These are related to the ancillary data and the flags themselves. The ancillary file would include the quality scores from some of the quality control procedures for the radiometric data. These would include the CLIP scores from the specific procedure, and then the flags would include the actual binary flags. Next slide, please. Then we have the remote sensing reflectance, mean remote sensing reflectance, and standard deviation of the remote sensing reflectance at 1 nanometer intervals from 350 to 900 nanometers or less is available. The remote sensing reflectance CSV is provided for each data entry, and the mean and standard deviation thereof are provided as available. Then we're looking at the method, variable, and unit keys describing the data headers, methods, and references. And for this, we have GLORIA variables and methods MS Excel workbook, which lists different tabs with the data headers, with the radiometric method, with the 3 types of laboratory method, and then another tab with the references. Finally, we're looking at the water quality attribute uncertainties for chlorophyll A, chlorophyll plus phaeophytin, TSS, and acetone, and these are found in the water qual and search CSV file. Then next slide, please. Looking at the metadata, we are finding referencing and identification information, site and condition information, environment information, radiometry information, and sample collection and analysis information. And this information is all found at the GLORIA Water Meta and Lab CSV file. Next slide, please. Looking at the radiometry in more detail, we can actually see that it's much more than only the instrument manufacturer, instrument model, latest calibration, and measurement method. We actually have a lot of information related to the viewing geometries and to the processing of the radiometric data itself. Next slide, please. Looking at the data headers, which are part of the GLORIA variables and methods MS Excel workbook, we can see that we have a list of different measurement methods for many of the different fields of metadata, and we're looking more specifically at the measurement method here. The measurement methods are numbered, and then they're followed by short descriptions. Looking at measurement method number 7, we see a fairly common measurement method with total radiance, sky radiance, and downwelling irradiance measurements on a frame deployed on a moving platform. We can see the same measurement method implemented in the picture to the right, where we can see the Terras-Ramsey sensors set up for the L-sky and LT measurements. Next slide, please. Then we have some less commonly used methods, and we're looking, for example, at method 14 there, where upwelling radiance measurements below the in water were collected, and then downwelling irradiance measurements in water were collected. These were only used for the depth information from in-water profiling from a moving platform, and then the ES actually used for the calculation of the remote sensing reflectance was simultaneously recorded from the same moving platform very close to the profiler deployment. And we try to accommodate every data contributor's exact measurement setups in this overview. Next slide, please. Looking at our example of radiometric method number 7, we can see that we have the overview of the method actually lists the method number 7, the methodology, LT, L-sky, and ES measured on a frame deployed on a moving platform, the Terras-Ramsey sensors, and then 2 different types of references. The first type of reference is the approach. This provides a reference to the theoretical basis for the measurement approach. And here we are looking at Mobley 1999 and Mobley 2015 for the viewing geometries and the correction of the reflected sky radiance. Then we're looking at another set of references for the applications, and these references show the application of this measurement method in detail. Next slide, please. Looking at the chlorophyll methods, we can see a lot of different information in the method summaries, ranging from the dataset ID, methodology, short name, and filter type to the approach and the applications. And something I would like to emphasize is that we can already see a lot of information from the methodology short name. In this case, we're looking at LabISA INPE chlorophyll SP. LabISA INPE stands for the organization. Chlorophyll stands obviously for the chlorophyll A measurement, and SP stands for spectrophotometry. And to look up any of these methods, you will only need the dataset ID and the methodology short name, and this will result in a unique combination to look up these methods in the GLORIA variables and methods overviews. Next slide, please. Looking at the TSS methods, we can see a similar picture. We have a dataset ID, methodology short name, filter type, measurement technique, approach, and applications. Next slide, please. And the picture is, of course, similar for the CEDAR method. There we have the dataset ID, methodology short name, filter type, measurement technique, instrument manufacturers and models, the approach, and the applications. And with this, I'm actually handing off the presentation to Moritz.
Great. Thank you very much, Daniela. Now, the central variable of our dataset is the remote sensing reflectance. So we've only accepted data for submission that included remote sensing reflectance. And now I'm going to show you how we were going about quality control of that particular variable. And the screen on the right here shows all our spectra, so 7,000 and some data points. And this is sort of a summary graph that we've created. And it shows a lot of information in one panel that is relevant for this quality control effort. And so I'm just going to go through this and tease the graph apart a little bit over the next few slides. And so I've just split this graph into two portions to show up better on the screen here. So the panels show the map where the samples were taken. So and these graphs were created both on individual spectra, on individual sampling instances, and also as an overview by collaborator or by data contributor. So these are my own samples here from New Zealand. And on the left sort of half of the screen, we see the map view, the radiometry, the component radiometry, so the downwelling irradiance, ED, and the LW, upwelling radiance. And these, whichever panels are filled in, depends on the measurement method. So L-sky would be, was not applicable to my method, and neither was LT. And on the right-hand side, the big panel there is the reflectance measurement, and the sort of the transformation of each individual spectrum to the human vision color space, and the lines in the spectrum are colored by the dominant wavelength of each measurement. And then on the bottom, it shows histograms of the water quality measurements that are associated with this data set. So when we got in the first data, really happy that the data looked really clean, looked really nice, and we thought, yeah, this is going to be easy, especially since Nima and his collaborators had worked with this data before. But of course, the devil was in the detail, and we looked when we looked at these summary plots, we could see that there were certain problems in all of the data sets essentially, and especially often related to the component radiometric measurements, because they had not been quality controlled as thoroughly as the reflectance by many of the contributors. So in this plot here, we see some of the data in the downwelling irradiance, so the ED measurement here. Those variable names, by the way, are slightly different to what the GLORIA variable names are. We ended up changing some of the names. So the ED shows some spikes here, individual values that were just out of range. In the reflectance spectra, the colorful spectra there on the right, in the right half of the screen, you can see that there's some negative values as well. And so those things were sort of indicators that we could look for fairly systematically and write code to identify those and either remove those spikes or remove the spectra if needed. But then there were also more subtle problems. So we come across spectra that kind of look wrong. In this case, there was a spectrum here that had a peak at 500 nanometers, so beginning of the green range, but also a lot of blue light around 400 nanometers, and which is unexpected. So normally when we see a lot of blue light, we wouldn't expect a green peak at the same time as well, because blue light is indicative of very clear oligotrophic waters. So this spectrum would be a candidate for saying, well, there's some measurement errors. But then looking at the sort of the progression, the nearby spectra from the sampling campaign, and the spectrum looks similar but slightly different. So the saddle in the 400 nanometer region is disappeared, and we see a decline, or we see a lower value there that looks closer to what we would expect. And yet the next spectrum there, again, similar, but perhaps slightly more realistic from our expectation point of view. And then we end up with a spectrum that perhaps we wouldn't have thought anything wrong of. Again, nearby from the same sampling campaign. So, oh, here's one more that just shows this progression. So it was clear that we needed some help, and we needed an approach to identify spectra that could be wrong, but that could also be right. And here are some of our sort of indicators of some of our findings of weird spectra or problems that we discussed. The way we discussed this is we had a great wealth. Of course, we had at that time over 50 principal investigators to provide data from their sampling campaigns. And we got together in a workshop. So we discussed features, we discussed spectra that looked like this. So we had the top left here, this blue case spectra that might be too blue, too bright. We had spectra that showing the blue tail, so that showed a very high value in the blue and then a decline. We had spectra that showed a lot of noise. We had spectra that had some baseline shifts that looked sort of okay, but there were many negative values, like the one in the bottom row, second from the left, and spectra that just seemed elevated, like the one bottom row, second from the right, baseline elevation. And so we got together in a group in a Zoom meeting and went through all these spectra and tried to find a methodology that would work, that we could essentially quality control this data set. And what we came up with is that we really did not feel like excluding or reprocessing any of this data, because first off, we couldn't be sure that these spectra were actually unrealistic. We all have our areas of expertise and our experience, but for all we know, there could be optical properties that we had measured that realistically cause these shapes, but that we didn't expect and that we didn't know about. So we felt really, really strongly that we did not want to modify any of these spectra or outright exclude them just because we didn't expect these shapes to be. And so we came up with a flagging approach. That said, there were some spectra that were actually outright that we felt 100% that these needed to be excluded because they were faulty, that showed a lot of gaps and showed very unrealistic shapes. So we came up with a flagging procedure, and this is table 2 from our manuscript. And so we were identifying many of those features that I showed in the previous slide that we would write code to objectively identify. And those were, for example, noise in the data, so a high frequency variability. There were baseline shifts that shifting the data up from the baseline or down below 0. Oxygen signals, so a peak in the sort of 760 nanometer range, if I'm remembering this correctly, which could show some problems of skylight corrections. These negative slopes in the UV, and then we felt, okay, so these were sort of formulaic quality issues that we could detect with code, but there are also a lot of quality issues or potential quality issues that we identify that we couldn't quite write a procedure to identify. And so we farmed out all 7,500 odd spectra to the participants in this quality control effort and had every single spectrum looked at and evaluated with respect to, does it look okay, or does it look maybe somewhat suspect, and identify why it looks suspect. And so the one above the bottom line here, suspect 226 spectra, were identified with our expertise in a process that we called expert elicitation as potentially fraught with measurement problems, but we weren't 100% sure. We didn't want to exclude those data points. And so we retained a maximum number of spectra, but we're providing this flagging. In the end, about 1,700 spectra were flagged with one or more of these flags. Also like to add that we conducted a couple of more advanced quality control calculations here, for example, the QWIP method and the 3C method that I won't go into detail here, but that are also very well documented. Now, one of the things to note in these quality control flags is that although they were determined using objective sort of code on all of the data, we did set some, these are binary flags, by the way. So these are either there's noisy red applies or it doesn't apply. So in order to achieve those binary flags, we had to set some thresholds, for example, where the noise level at which we would set this flag. And these noise levels were somewhat subjectively set by us looking at the distribution of noise levels and the shape of the spectrum. So if you don't like these noise levels, you can ignore the flag, or you can go online and download the code or write your own code. But all the code for quality control that we have has been put onto a repository by Daniel, and he'll probably show you in his part of the presentation how to get that and how to reprocess it. But all the information there is open, so you could reprocess and get at those values. This is what the quality flag file looks like, GLORIA QC flags.csv, and it has as many rows as we have data points in our data set, and they're identified by the GLORIA ID. Most of these are 0 flags because the data looks great, and some of them have a 1 in one of the columns. So it's pretty straightforward to use. And with this, we've hoped to have produced a very user-friendly, a very complete data set that is their analysis ready, but that you can still slice and dice according to your needs. So the vast majority of data looked really, really great. So that was awesome. We've, as Daniela showed, included so much ancillary data and information about how the data was how it was measured, and under what conditions, that it would allow you to really filter this data set and get out the subset that you need for your analysis. And obviously, we found that that many of the radiometric protocols perhaps weren't 100% followed or weren't fully specified. So we would recommend that effort towards standardizing protocols and best practice would be well spent, both in developing these and in making sure that people know about them. And that brings us to the end of my presentation. I'll hand over to Daniel to show us some code and some of the direct applications of this data set. Thank you very much. Happy to take any questions at the end. Daniel, I suppose you want to share your own data?
Yes. Let me share. Okay, can you see my slides here?
Yes.
We just need to go into presentation mode.
It's good now. Just go to full presentation.
I tried to put
there you go.
presentation mode here.
It's good.
Working. Yeah, it's working. Okay. So hi everyone. My name is Daniel Maciel, and I am from a Brazilian National Institute for Space Research, and I will show you guys now how to use some programming language to access, to explore, and work with GLORIA data. Can you hear me well? It's good. I don't know if my internet connection is so good, but
we hear you well.
Yeah. Good. So we're gonna see how to use some programming language to work with GLORIA data, but in this case, we're gonna see how to use R. But we can go to Python, to Google Earth Engine, well, using JavaScript or Julia, or any programming language you want to use. So, but let's first start with a case study, something like that. So let's imagine in this reservoir here, how to retrieve, or how I can retrieve chlorophyll concentration for this very eutrophic reservoir. It's a reservoir here in Brazil, in São Paulo city. And how to retrieve chlorophyll concentration without any in situ data? Well, we can try a first approach, a first map, using the GLORIA data. And absolutely, of course, in situ or a validation data, it's very necessary for algorithm performance assessment and things like that. So we're gonna see how to use GLORIA data to create a map of chlorophyll concentration for this specific reservoir here. So we know that remote sensing reflectance could be related to chlorophyll concentration. So that's what we're gonna see here. So the first step that we need to do is to download the data. After that, we need to use the hyperspectral data to simulate. In this case, we want to create a map for Sentinel-2. Well, we need to simulate for Sentinel-2 bands. Then we can develop an empirical or a machine learning or a semi-analytical model. And finally, we can apply this to satellite data and have our maps or our time series and things like that. And we're gonna see how to do that using R. In this case, RStudio or whatever. But of course, we can't do that in 10 minutes. Well, at least now we have 8. But we'll just see quickly how we can do this analysis. So starting the data set, as Danielle and Iman Martz commented, is available on .gs, so you can go there, download the data set, and click in the link, download the zip file. Or you can use, of course, when you download, you have something like that, all the tables, and the tables that we really want to develop our model, or the table that we mainly want, is the remote sensing reflectance and the meta and lab. And they look like the 2 main tables that we need. So we can do this by using R. Using this code here, we can download the data using just this link here, unzip the file, and read the necessary tables. So it's pretty easy. And using this code, we can download and load the tables we want. So after that, the tables will like these things. Here is the meta and lab table and the GLORIA remote sense reflectance table on the right side. So after we download the data, we need to convert the hyperspectral data to sensor-like bands, or we need to simulate based on the sensor respective spectral response functions. So this package here called band simulation, you can apply these filter functions to some sensors. In this case, we want to apply to MSI, to Sentinel-2 MSI bands. And then we can have results something like this. This is an example for two GLORIA stations with very different values of chlorophyll concentration. And we can see here, these red points are the MSI simulated bands, and the black points, or the black line, is the hyperspectral remote sensing between 400 and 900. And we can see that more chlorophyll concentration, we can have this peak in the remote sense reflectance, that we can use this to create an empirical model and then estimate chlorophyll concentration. So yeah, knowing that, and this figure here, I like this figure too, because we can see the difference in the water color and in the remote sense reflectance shape. This is for example in the Brazilian reservoir here. And well, knowing that, we can start our exploratory analysis based on simulated remote sense reflectance. And we can use a very well-known index, that is the NDCI, or the Normalized Different Chlorophyll Index from Michelin in 2014, that use the red edge and the red bands to create an empirical model and have a very good relationship with chlorophyll concentration. And we can see this here in this plot. We have right here the NDCI +1, because I am applying the log, so we need to sum on to don't have negative values, and chlorophyll concentration with a R² of 0.6. It's like okay. And the NDCI was widely used to retrieve chlorophyll concentration. So now we know that using the GLORIA data, we can have like a very good relationship, or a good relationship between DCI and chlorophyll concentration. And we can use this code here to create an empirical model based on a trained data set. Then we can validate this model and plot the results to analyze how are the errors that we are getting from there. And this code create a model and plot the results based on a validation data set, all using only GLORIA. And here's the results. So you can see that we have an error of almost 60%, but think that we are using a very simple empirical model. So it's not like perfect, but it's good, because it's not bad for an empirical, very simple algorithm. And we can then apply this to our satellite data to have like an idea of the chlorophyll concentration in our study area. So we can now apply the empirical model that we have generated. In this example here, for the same image that I showed you guys before, this was applied in R using the stack image provided by the Microsoft Planetary Computer that are stored in Microsoft Planetary Computer and organized in the stack platform, is the Spatial Temporal Asset Catalog. And we can access free of charge these images using R. These are images corrected by a Central Core. That's not so good for water, but it's good to show an example of application here. Okay, and we can have a map that is correctly showing where the chlorophyll concentration is high, like very high values, more than 600, 700, but it's expected for these locations in a case of a very big, a very high bloom. And we can also create time series using the maps created. So this was also generated using R, and we can see that we can have a time series of chlorophyll concentration for this reservoir. So it's again, it was, oh, this is the time series for that we can get using R and all the GLORIA data. And next slide, Morris, please. I'm not seeing anything.
We can hear you, Daniel.
Yes. Just to comment, can you hear me?
Yes.
I'm sorry. And just to, if you want to know more and if you want to learn how to use remote sensing and GLORIA data for aquatic remote sensing applications in the next month in the rocking limnology workshop, we are going to teaching a free 3-hour course on aquatic remote sensing using GLORIA data and with some analysis that I showed here. And if you want to register, you can click on this link here. And that's it. Next, I think that the next slides are your.
Sure, I'll speak to them. Thank you.
Okay.
Perfect. Well, thank you very much, Danielle. That is very cool. The most important thing is that it's actually being used, and you show us how to do it, and that's very good that the code is available and the help. So perfect. Though there's a few bits of information available out on the GLORIA dataset. The data itself is hosted on Pangea, and just Googling Pangea and GLORIA would get you there. But we really recommend to also read the manuscript, the paper that we published in Scientific Data. Now, you may come across this article first before you look for the data, and then you wonder why this data descriptor does not have an obvious link to the actual data set. And that's the way Scientific Data does it. So when you go to the website of that article, you don't see a download data button. So I've been getting several emails of people saying, oh, where's this actual data hosted? And so you have to read the article and then go to data availability, and then there's a link to one of the citations. And I think it's citation number 8, reference number 84 in this whole paper that contains the link to Pangea. And so that's how you get to the data down on the Pangea page on the screen there in the middle panel. Right at the bottom is the download to the CSV file, and you can freely download it. And as of yesterday, it was downloaded 274 times. Now, the Nature portfolio group of papers of journals has invited us to write a blog article on behind the paper, and Daniel has taken that on as a lead, and he's written something about what it takes to actually take these measurements in inaccessible and difficult parts of the world, and going to places that then no measurements have ever been taken before, or perhaps running really long time series. And there's some cool pictures on there and some links to some video footage from various parts of the world. And also, as you can see there scrolling by on the right-hand side of the screen is an Instagram reel that the Nature communications team has put together on GLORIA that was released, I think, about 2 weeks ago. With that, I'll close the presentation. Our contributions here, when we share this presentation, here are the actual sort of links to the various bits that I've just showed, and also the code repositories. These are all linked in the paper, of course, as well, but for completeness here on this presentation. So thank you very much for getting up early, staying awake late, or just listening to this in the middle of your day, and we'd be happy to take any questions.
Wonderful, Maurice, thank you very much. We do have one question so far in the chat. Masuma Chowdhury asks, are you going to continue updating and releasing the data in 2023 and beyond?
Well, that's a great question. And just as a sort of a flashback to Nima's presentation, the effort of GLORIA was pretty grassroots. So we haven't been funded by a central agency, by a central funding source. So we've all been putting our own time in. So we really hope that this could be picked up further, but we don't have a formal arrangement at this time. But we'd love to sort of spin the machine up for this to be continued. Any of my collaborators have any comments on that?
I can add quickly something. Yeah, just what you said, Moritz. I echo that. There are no plans at this point to update this data set. However, Daniela and my team currently are working on putting together inherent optical properties, sort of as an augmentation to a subset of this GLORIA database or data set, and I'm hoping that we would release that data set, which again, it would include absorption and backscattering spectra associated with some of the data in the GLORIA, and the hope is that we would be able to release that in a year and a half from now.
Okay, great news. Good luck. And if anybody has spare change laying around that you would like to throw their way, I'm sure that the presenters would be delighted to chat with you. We do have another question from Felipe Lobo. What are the criteria or specifications to add data into GLORIA?
Yeah, so as we discussed just now, we don't have a process of maintaining and updating GLORIA as yet, and that's something I think that we would want to continue to discuss in a forum. Now, there is a way that data sets such as this on Pangea can be updated. They would the criteria for adding data into GLORIA is that you would, for us, when we did this initial call, that you would have a high quality remote sensing reflectance spectrum and at least one water quality attribute, be that chlorophyll, suspended sediments, Secchi depth, or CDOM. So in any combination we accepted, and then we would bug you to get us as much information on your data as possible. And so Felipe, if you're interested in continuing this effort, then please get in touch, and we might pass on the baton or work with you on adding more data.
Moritz, was there also not a criteria to have a matchup with a flyover of the satellite?
No, not for this particular one.
Okay.
We wanted as many data points as possible, and yeah, Nima, do you know how many actual matchups we have in the new GLORIA dataset?
It varies depending on the satellite, but for Landsat 5, for instance, Danielle, you can correct me if I'm wrong, but we probably have about 200. For Landsat 8, we have about Landsat 7, we have about 500. For Landsat 8, about 200 to 300 matchups. For Sentinel-2, about 2 years ago, we had about 200 matchups. So it has to be updated. Danielle is working on it. My team is working on matching GLORIA datasets with MODIS, MERIS, VIIRS, you name it. So we don't really have the numbers, but the kind of the numbers that I gave you, that kind of give you some ideas about different satellite missions over the years.
Great. And as I put in the chat, we understand if you need to leave us now, but if the presenters will hang in for another 5 minutes or so, we can ask some additional questions. Are there any other questions from anybody in the audience? You can either type it in the chat or unmute and ask your question directly. I'm seeing Aaron Urquhart from NASA asks, how will this work inform upcoming hyperspectral observatories, such as PACE, GLIMMER, etc.?
Yeah, I can take that and have my collaborators chime in. But thank you, Aaron. Awesome question. Of course, hyperspectral data from in situ observations are the key to calibration and validation of spaceborne hyperspectral sensors. So while what we're really hoping, of course, is that this data set spawns what we've just been talking about, a more proliferation of collection of these data for the time when the hyperspectral sensors are actually operational, in addition to the ones that are already out there that have already been informed by our data set. But you mentioned PACE and GLIMMER, upcoming launches that that would benefit from simultaneous measurements, of course. But these measurements that we've produced here are really the key to explore, to utilize the full spectral information that these satellites will sense, and so to get a head start on algorithm development, for example, using a whole spectrum.
Wonderful. Any other comments, Nima?
I second that. I think what drove us, one of the things that drove us to put out the GLORIA data set is just the need for the inclusivity of our community, and being able to put out the data sets for everyone out there, and many different rural areas to advance the state of the art in our community, and hopefully be able to essentially see further sort of expansion of these kind of activities, data sharing in our community, to be able to advance products, improve the quality of water, the products from satellite measurements in the future, and communicate the caveats and potential issues to the end users and scientists in the future. So yeah, that's all I had.
Okay, we have, Aaron seems pleased with that answer. We have one final question by Banyad. Is the effect of spatiotemporal autocorrelation included in the data analysis in MDN and so on?
I guess, yeah, thanks, Bonyad, for the question. That's, I guess, directed to me. So yes, we understand there is a spatiotemporal correlation within the data sets. There were many campaigns, and in each campaign, the data sets were collected and then especially temporally close to each other. So we are aware of those kind of correlations within our data sets. For the performance assessment, if you consider a holdout approach, there will be a spatiotemporal correlation, which will be potentially beneficial to the reporting of the performance, and potentially optimistically communicating those performances. However, there are other ways to evaluate the performance by separating out those data sets according to their region that they've been collected, to enable a more independent assessment of the performance of a model. MDN being one example, but in reality, we definitely need to have an independent performance assessment approach, and again, one of which would be this leave one out approach that we have used over past a year and a half or so. But there are other approaches to minimize that spatiotemporal correlation within the data set, which is unavoidable, because again, people go out, collect data on the same day, and the data would be correlated no matter what. It's just a matter of how to treat the data and how to make sure that dependency is minimized is the key.
Great. Well, thank you very much. Please use your emoticons to make a reaction for our speakers today. We do thank all of our speakers for giving us this wonderful webinar. I do apologize for my voice or lack thereof again. And just in case you missed it, the recording for today's webinar will be found on our website. I have put the link to the website page in the chat. It should be up there tomorrow, sometime tomorrow morning. So thank you very much again to our presenters. And on behalf of GEO AquaWatch, I hope you all have a wonderful day. Thanks for coming.